In this video, we are going to see the steady state stability analysis for small disturbances using swing equation. We know this is the swing equation. Actually, PM minus PE, we had already derived PE is equals to PM sin del. So I'm replacing PE with PM P max sin del. Now let us consider a small deviation del del in power angle. So del is equals to del naught plus del del. I'm substituting this small deviation in the swing equation to get h by pi f naught is equal to d square del naught plus del del by dt square is equal to Pm minus P max sin del naught plus del del. Now, this I can write as h by pi f naught d square del naught by dt square plus h by pi f naught d square del del by dt square is equal to Pm minus P max sin of a plus b. I am expanding it sin a cos b plus cos a sin b. Sin del naught cos del del plus cos del naught sin del del. Del del is very small since the steady state stability analysis we will be dealing with small disturbances. So del del will be very small. We know if del del if it is negligible that is equals to 0, cos 0 is 1 and sin 0 is 0. So cos del del is approximately is equal to 1, sin del del is approximately is equals to del del. Now, so I am replacing here. I am replacing this cos del del with 1 and sin del del with del del to get this equation. Now, at initial operating state, that is del del is equals to 0, I will be getting h by del pi f naught d square del naught by dt square is equal to Pm minus P max sin del naught. Then the linearized equation in terms of incremental change in del is, that is the changed additional terms added, h by pi f naught d square del del by dt square. This minus I am taking this side, so I will get plus P max cos del naught del del. Now this P max cos del naught can be written as PS. So h by pi f naught d square del del by dt square plus PF PS del del. Here dt square PS del del. So now this is the equation we got. Now the solution of this equation is s square is equals to minus pi f naught by h ps, where when ps is negative, we have one root in the right half s plane and the response is exponentially increasing and stability is lost. When ps is positive, we have two roots on j omega axis and the motion is oscillatory and undamped. The system is marginally stable with a natural frequency of operation omega n. So let us derive the equation for natural frequency of oscillation. S square is equal to, when the system is positive, S square is equals to pi f naught by h into ps. We know that S is equal to j omega. So S square will be is equal to j square omega n square. J square is equals to minus 1. The negative sign, actually here we had a negative sign, and j square is equals to j square is minus 1. This minus and this j square gets cancelled. So we get omega n square is equals to pi f naught by h ps. Omega n is equals to square root of pi f naught by h into ps. This omega n is the natural frequency of oscillation. The range of PS is positive, lies between 0 to 90 degrees with a maximum value at no load, that is del naught is equal to 0. Now, as long as there is a difference in angular velocity between rotor and the resulting rotating air gap field, induction motor action will take place between them and torque will set up on the rotor, tending to minimize the difference between the angular velocities. This is called damping torque. The damping power is approximately proportional to speed deviation. So PD is equals to D into del del by dt, where D is damping coefficient. If damping is considered, then the swing equation will become h by pi f naught d square del del by dt square plus d del del by dt plus ps del naught is equal to 0. Now in this equation, I am taking h by pi f naught common and sending to the other side. D square del del by dt square plus pi f naught d by h d del by dt plus pi f naught by h ps del del is equals to 0. Now considering this equation and comparing with the standard second order equation which we will learn in control systems, d square del del by dt square plus 2 eta omega n d del by dt plus omega n square del del is equals to 0. If you compare the second equation and third equation, 2 eta omega n is equals to pi f naught by h into d, omega n square is equals to pi f naught by h into ps. Upon solving, what we will get? Eta is equals to d by 2 square root of pi f naught by h into ps, where eta is the damping ratio which does not have any dimensions. Now considering the characteristic equation, s square plus 2 eta omega n s plus omega n square. For normal operating conditions, this eta is equals to d by 2 square root of pi f naught by h ps will be less than 1. And the roots of the characteristic equation will be complex. That is S1 comma S2 is equals to minus eta omega n plus or minus j omega n into square root of 1 minus eta square. This omega n into square root of 1 minus eta square can be written as omega d, where omega d is the damped frequency of oscillation. From this, it is clear that positive damping, for a positive damping, roots of characteristic equation having negative real part, synchronizing power coefficient PS is positive. The response is bounded and the system is stable. So this is the small disturbance steady state stability analysis using swing equation. Thank you.